Chemical bonds differ mainly in how electrons behave. Ionic bonds transfer electrons, covalent bonds share them, and coordinate bonds donate a whole pair from one atom. Keep that distinction clear because it explains many properties and helps with ICSE reasoning questions. So far, we've built the foundation step by step: why atoms bond, how ions form, how covalent sharing works, and where coordinate bonding fits in. Now we'll bring those ideas together so comparisons become clearer, more exam ready, and easier to remember. Why compare bond types at all? Because the way atoms hold electrons affects how a substance behaves. It helps explain high melting points, solubility in water, and electrical conductivity. Once ionic, covalent, and metallic bonds are compared side by side, exam answers become much more logical. The main difference is what happens to the electrons. In an ionic bond, one atom gives electrons completely, and another atom accepts them, forming oppositely charged ions. In a covalent bond, atoms share electrons, so both nuclei can count the shared pair towards stability. In a coordinate bond, the shared pair comes from only one atom, while the other atom accepts it. The process is different, but the goal is the same: a more stable electronic arrangement, often like a full outer shell. Ionic bonding is based on electron transfer. A metal atom, such as sodium, has a loosely held outer electron. It loses that electron and becomes a positive ion, or cation. Na becomes Na+. A nonmetal atom, such as chlorine, accepts the electron and becomes a negative ion, or anion. Cl becomes Cl-. The bond, however, is not the transfer itself. It is the strong electrostatic attraction between opposite charges. Sodium ions and chloride ions attract, forming sodium chloride. Covalent bonding solves the stability problem by sharing valence electrons instead of transferring them. This usually happens between nonmetals because neither atom easily gives electrons away. Each shared pair counts toward the outer shell of both atoms. One shared pair forms a single bond, as in hydrogen. Two shared pairs form a double bond, as in oxygen. Three shared pairs form a triple bond, as in nitrogen. In general, more shared pairs make a shorter, stronger bond. This sharing pattern builds molecules such as water, methane, and carbon dioxide. Coordinate bonding is a special type of sharing. Here, the shared electron pair comes from just one atom. The donor must have a lone pair available, like nitrogen in ammonia or oxygen in water. The acceptor must be electron deficient, with an empty orbital, like H+. The donor's lone pair is shown moving toward the acceptor with an arrow. Once the bond forms, it behaves like an ordinary covalent bond because both atoms now share the same electron pair. A quick way to predict the bond type is to look at the elements involved. When a metal meets a nonmetal, the metal usually loses electrons and the nonmetal gains them, forming an ionic compound such as sodium chloride or magnesium oxide. When nonmetals bond with other nonmetals, they usually share electrons, as in water, methane, or carbon dioxide. Coordinate bonds are the special case. One atom or ion donates both electrons from a lone pair to an electron deficient partner, forming species such as ammonium or hydronium. Electron dot structures are more than drawings, they show the bonding process. For an ionic bond, show the final separate ions with brackets and charges. For a covalent bond, place the shared electrons between the atoms. For a coordinate bond, use an arrow to identify the donated pair. In ICSE answers, show only valence electrons, use dots and crosses clearly, and place every outer electron correctly. Small diagram mistakes can cost easy marks. Now connect bonding to melting and boiling points. In ionic compounds, positive and negative ions are held in a giant lattice by strong electrostatic attraction. A lot of energy is needed to separate them, so ionic compounds usually have high melting and boiling points and are solid at room temperature. Covalent compounds are made of molecules. The bonds inside each molecule are strong, but the forces between molecules are usually weak. That is why many covalent substances melt and boil at lower temperatures and may be gases, liquids, or soft solids. Electrical conductivity depends on whether charged particles can move. In solid ionic compounds, the ions are locked in a rigid crystal lattice, so charge cannot flow. When the compound melts or dissolves in water, the ions become mobile and the substance conducts electricity. Covalent compounds are different. Their particles are usually neutral molecules, not free ions. So, sugar dissolved in water, for example, does not normally complete an electrical circuit. Solubility also depends on the attractions particles can make with a solvent. Ionic compounds such as sodium chloride often dissolve in water because polar water molecules can surround and separate the ions. They usually do not dissolve well in nonpolar organic solvents. Many covalent compounds show the opposite pattern. They are less soluble in water, but dissolve more readily in organic solvents, especially when they are nonpolar. Their physical states also differ. Ionic compounds are typically hard, crystalline solids. Covalent substances may be gases, liquids, or soft solids, with network solids like diamond as exceptions. The link between bonding and properties is structure. In an ionic compound, melting or boiling means overcoming many strong attractions in a giant lattice. In most covalent compounds, the strong bonds are inside each molecule, while the attractions between molecules are weaker. Coordinate bonds, once formed, behave like ordinary covalent bonds. So the key question is, are you dealing with forces inside a molecule or forces between particles? For comparison answers, use a consistent formula, definition, electron behavior, elements involved, example, and property reason. Ionic means electron transfer, usually from a metal to a nonmetal, forming ions, as in sodium chloride. Covalent means electron sharing between nonmetals, forming molecules, as in water. Coordinate means one atom donates a lone pair to another, as in the ammonium ion. For reasoning questions, always connect structure to movement. Molten ionic compounds conduct because ions are free to move. Covalent molecules usually do not, because they lack mobile ions. To wrap up, remember the core distinction. Ionic bonding transfers electrons, covalent bonding shares electrons, and coordinate bonding uses a donated lone pair. The properties of compounds follow from structure, particle type, and whether charged particles can move. Use this comparison framework to handle ICSE style diagrams, reasoning questions, distinction tables, and scoring answers with confidence.